Okay, I think we'll go ahead and start the day. Welcome everyone to our 2020 virtual open house featuring the capabilities of the Nanomegas and the Topspin. And Nanomegas A-Star and Topspin, as well as our Protochips system. Thank you for joining us today. Feel free to ask any questions you have in the moment in the chat, and hopefully we'll be able to get to them pretty quickly. And then I think we're going to try to allow plenty of verbal Q&A time at the end of each presentation. May as well make use of this day and this time. And with that, I'm going to go ahead and hand it over to Kristen Maitland, who is our director here at the MIC.
Thank you, Ashlyn. I'm Kristen Maitland. I'm the director of the Microscopy and Imaging Center, and I'm really happy that you've joined us this morning to hear about some of our new technologies that we have in the MIC. We have in the MIC, if you haven't been, I hope that some of you are already users and familiar with our instruments and our staff. But we really are focused on electron microscopy and light microscopy, focused on research at Texas A&M and in the region. So we are always happy to partner with faculty and research staff in order to be able to provide the imaging capability that you need for your research. And so with regard to electron microscopy, we have 4 transmission electron microscopes, and also 2 scanning electron microscopes that are really customized and set up for various applications. Additionally, if you're not aware of it, we are in the process of ordering and installing a new cryofib sim where we can do SEM imaging of surfaces to build up a 3D tomographic image. And so in addition to electron microscopy, we have quite a few light microscopes, and we typically will have different activities and workshops and now virtual seminars where we can share with you some of the capabilities that we have, both that are ongoing and new and incoming technologies. So always please take a look at our website and the different events. We try to promote our activities through our user list, but also through other email lists throughout the university. So I hope you are familiar with the information that is coming out from our center so that you can stay on top of the activities that we have going on. I want to thank Ashlyn Montgomery and the rest of the staff. Also, Avery McIntosh did a lot to set up the video tours that we have arranged for this afternoon. And so I hope you can join us. Feel free to come and go if you have other commitments, but we will be going this morning until about 10:30. And then also this afternoon, we'll start our tours at 1:30, and we'll have a demonstration of the A-Star at 2 o'clock. And also, just so you know, the talks will be recorded and put on our website. So if you think that you know somebody that might be interested in the technologies after you hear about them, please share those links so that others can find out about them as well. Another thing I wanted to make sure that people are aware of is that we do have a small seed grant program where if you have a new project that you want to try out and you're not sure if it's going to work, and if you're a faculty member and you're unsure about having a student trained on an instrument, if you're not sure that the project will work out, we do have a seed grant program where we basically waive the staff time to try out a new technology or a new application with an instrument. And so just let us know if you have questions about where to find that information. And then finally, I'll say that we have the most amazing staff, and anytime that you are just wondering about how to get the data that you need, we really have a great resource within our center where if you contact anyone, they'll connect you with the right person, and they are very helpful and willing to help you achieve your research goals. And so thank you to all the MIC staff that are on the call, but also I encourage you to get to know them if you don't already. Let's see. I will go ahead and introduce our first speaker. So this morning we're having 3 talks. The first is from Protochips, which is our new, the company that has developed the new thermal control holder that we have in the MIC. Following that, we'll have a presentation from Nanomegas. And then Dr. Kelvin G from Material Science and Engineering will be giving a talk on his research. And really, he's been a great partner for the MIC in helping us acquire these new technologies into the MIC, and also just a great advocate for the MIC and a great collaborator. So first off, I'll go ahead and introduce our first speaker. Remy Berthier is from Protochips. He's based in France, and so we are very appreciative that he's able to participate with us this morning. And he's an application scientist at Protochips Fusion System, and he'll be talking about advancements in MEMS-based in situ TEM heating. So I will turn it over to you, Remy. Thank you very much for joining us.
Thank you, Kristen, and thank you for the MIC for making that talk possible. So I'm Remy Berthier. I'm the application scientist in Europe, specialized in the fusion heating and biasing holder. And today I would like to present you the advancement in MEMS-based in-situ TM heating. So as Kristen said, this system is available at MIC. And I'm going to describe some of this, its function in the first part of my talk. And in the second part, I would also like to present some of the key developments that were done recently that can be added to that system. Okay. So first, a quick look at what is in-situ TEM. Technological advances over the last decade have led to the development of this in-situ TEM techniques. Those techniques allow researchers to interact with a specimen by applying a stimuli within the TEM column directly on the sample. And this allows to study dynamic and dynamically changing systems and use the TEM as a real-time nanoscale laboratory. This allows to fill in missing steps in the dynamic and evolving processes that could not be observed by any other means. An easy analogy that we could make is from photography. And as you see on the top right, this is a painting of the pre-photography era that shows a horse running with the 4 feet off the ground. And it's only after 1878, I believe, that some of the photographs of a horse running were taken, and it was possible to see that at no point during its run would the horse lift all 4 feet off the ground. And likewise, in-situ TEM allows us to fill in the missing gaps in evolving processes and do it at atomic resolution in a way that was never previously possible. So technically, what is possible then with a heating and biasing system inside TEM? In this example, you can see some control of reaction kinetics, the recording of some phase change in crystal, and the growth at atomic resolution of nanowires, or even for electrical application, the observation of nanoelectronic in action. Basically, the variety of application is limitless. So what is the Fusion Select system itself? It's a TM holder which is upgradable, and what I mean by that is that you can select some key features that you require for your research and only purchase what you need. And as research evolves and as the needs of a laboratory evolve, it's possible to unlock all of the capabilities of a system over time without any loss. I believe currently at MIC, you have the heating double tilt holder setup. So for example, we can think in terms of future projects to consider electrical package or simultaneous electrical and heating package if a given project requires it. In terms of capabilities, one of the key aspects of the Fusion Select system is its accuracy. So when we say MEMS-based holder, it's because the active element inside the holder that will apply the stimuli to the sample is the MEMS chip that you see in the bottom left. And when we provide the chips, every single one of them is tested by infrared imaging, so that we can ensure the chip is working as expected and produce a calibration file which is provided with every single chip. So we know every chip that we provide, we know how to hit it and exactly what temperature it's going to reach. And that allows to have more than 95% accuracy on the temperature of the sample during a TEM observation. And on the image that you see on the bottom, on the video you see on the bottom right, it's in an SEM actually, with the same technology, and it shows the melting of Schottky glass with a very precise transition temperature. And this melting precisely starts at the temperature expected. Of course, as we're working inside a transmission electron microscope, it's natural to expect to maintain the capabilities and the incredible capabilities of a TEM, and that includes analytical power. And the way the holder is designed, the Fusion Select holder is designed, there is a lot of work done on the tip itself to minimize the shadowing and ensure that you can perform EDS without or with minimum loss in terms of detector exposure, even at 0 degree tilting. So this allows, in the case of the SuperX from Thermo Fisher, to obtain more than 80% detector exposure and more than 71% in the dual SDD from Joule. And of course, EDS can be performed at higher temperature, up to 750 degrees, which is more of a, an order of magnitude, because it ultimately, depends on the EDS system itself. So when we look at the MEMS chip itself and the active part of the MEMS chip, it's actually a suspended membrane. So this allows for the TEM beam to go through, but this suspended membrane comes in 3 shapes. On the most right picture, you have the suspended membrane in yellow with holes so that the TEM beam can go through, and there is no coating on it. So you can imagine depositing a fib lamella or floating a 2D material on top of it. There would be no background. You have really access to the vacuum in those holes. But if you want to look at, for example, nanoparticle, or if you want to deposit or sputter a thin film directly on the chip, you need some physical support. So you can use the silicon nitride coated chip to act as a support, mechanical support for the sample. And finally, in the left image, you have the carbon coated chip. And this carbon coating, which comes on top of the heating membrane, is the same used in C-flats technology from Protochips. And it's an extremely low contrast amorphous carbon layer, which allows to observe extremely small sample or extremely light sample with optimal accuracy. So now in terms of a case study, this example comes from a Nature Communication article and looks at hafnium oxide nanorods being heated and cooled down inside the TEM column. On the left picture in green, you can see the green is the monoclinic phase of the hafnium oxide, and as it's heated up to 600 degrees, you can see the emergence in red of tetragonal phase, which nucleate from twin boundaries inside this nanorod and propagates until the full nanorod becomes in a tetragonal phase. Then this mechanism and this phase change could be observed with atomic resolution, and it was natural to expect that upon cooling down the sample, it would switch back into its monoclinic phase. However, what they observed is that instead, the hafnium oxide was reducing into a metallic hafnium nanorod. And not only could they observe this this reduction process with atomic resolution, but they could also notice some of the bright spots that you see on the image, which are individual atoms and very small clusters of hafnium detaching from the nanorod. And this was, of course, done in real time in the TEM with atomic resolution. Another example of application and some of the incredible work that has been published recently is the growth of nanowires at atomic resolution inside the TEM. In this example, it's a gallium arsenide nanowire, which is being heated at 400 degrees C, and they could observe the building of a single atom layer of these nanowires, one at a time, one after the other. And they could see, if you notice on the movie, that basically it starts from the left, then from the right. It starts with the truncation of the previous layers. And once the layer is big enough, this truncation disappears and the layers finishes its growth. And they could observe more than 50 layers growing one after the other on that very footage. What they did after that in the same study and in a more recent paper is they observed the same nanowire growing, but this time in bird's eye view in order to have a visualization of the top surface of this facet and this nanowire facet. And they could see that at several points during the growth of that facet and over the growth of that single atomic layer, it was restructuring many times in many different manners. And by combining this observation of in situ TEM with calculation of the energy and the edge energy of that facet, they could demonstrate that it was basically following the lowest energy for that facet. So every time the edge was not favored in terms of energy, the facet would reconstruct and continue its growth until it was not favored again, and so on and so forth. So thanks to that, they've been able to explain and obtain better control of the growth of those nanowires at atomic resolution and observe the mechanism itself behind its growth. And this allowed them to select, for example, the growth of a given phase over another with extremely high precision, for example, to switch between two crystalline structure at will. So this was the fusion select system, and now I want to talk about some of the latest improvement done in the field of in situ systems. And this is Axon. So historically, TEM and in situ innovation have existed in silos. They were isolated from one another. And this disconnection was a big challenge because it was limiting the overall performance of every single party. And everybody, thought of a solution, but it never happened until Protochips released it last year. And it basically allowed to make those three elements communicate. By having the TEM columns, the detectors, and the in situ holders communicate and exchange information, you can basically automate the tracking of a given region of interest. If you consider, for example, a nanoparticle, by activating Axon on that nanoparticle, no matter what you do, it will maintain this particle inside your field of view and assist you in performing the focus adjustments and maintain the full resolution available despite any drift that could happen from any source, from thermal source, from mechanical source, from the TEM itself, for example, if you change mode. And it's robust also to any physical sample change. So if your sample, because you're doing in situ, and at the end of the day, you modify the sample and you make it morph into something different, the software will be aware of that and will consider it and will maintain the sample that you desire in your field of view, even if its shape is changing. And this is what it looks like. On the left, you see a core shell nanoparticle, It was known that upon heating, those core shell particle would crystallize into a monocrystal. However, because it was happening extremely fast over a very narrow range of temperature, it was very hard to capture precisely with the resolution necessary. And by activating Axon, it was possible on the first run to observe the growth of this single crystal, atoms by atoms, with unprecedented accuracy and unprecedented resolution without effort automatically. And similarly, on the right, you can see it's actually the ancestor of MEMS-based heating holder. It's a bulk heating holder that used to heat up entire copper grid for regular TM application. And in those previous systems, the amount of material that you heated was huge because you needed to use a millimeter-sized copper grid. So the thermal drift was incredible, and it was basically impossible to maintain atomic resolution during a live heating ramp. With Axon activated, this was made possible, and it was possible even in this older technology to maintain atomic resolution during active heating. And those facts are not limited to in-situ system, and they can be applied to classical TM holder as well. In this footage on the left, you see a strontium titanate lattice after being tilted into zone axis, and basically the beta tilt of this regular TM holder led to instabilities that took a long time to settle down. Using the same holder, the same system, the same sample, but activating Axon, it was possible to completely annihilate this drift and observe the resolution that was expected by the researcher instantaneously after tilting. And you can think that this can be also applied to cooling holders, like liquid helium holders, tomography holders, for example. You can remove waiting time when changing mode from TEM to STEM, changing voltage, acceleration voltage, all of those things that would induce drift in the regular life of a TEM users, those things can be removed. And as Axon makes those three elements communicate, it also synchronizes the information, and it synchronizes every available information inside the TM and the detectors. So in every single image that is saved and recorded and saved by Axon, you can find all of the metadata from the in-situ system, of course, from Protochips. You can find all of the data from your TEM, from magnification, scale, obviously, current, stage position, beam position, tilt, all of the metadata regularly available inside the TM. They're present in every single picture. And same goes for STEM detectors. And with the visualization software, Axon, you can also report the data much more efficiently because you can select which of those data you want displayed on the image, and you can prepare your reporting much more efficiently. And finally, every single image with all of the benefit I've just listed is saved into a lossless PNG format so that you can observe and look and work on those images in the software that you prefer. If it's Axon, it's okay. If it's something you're more used to, you can also move to that. The format is not proprietary. And as I mentioned to Kristen a bit earlier before the talk, one of the unexpected benefit of Axon in the current context and in this wonderful 2020 of a year is that Axon, because of the way it's designed, can act as a relay between the TM and the outside world, so that you can easily and safely share the video feed of what's happening in your column and share data so that you can perform and present experiments remotely and it facilitates presentation, demonstration, collaboration work by allowing those things to happen. So to summarize, Axon reduces the learning curve for in situ. It makes every single step of the way easier. It makes also in situ and TEM in general more powerful because it allows you to see every moment and see things that were previously not within reach. It makes data analysis much faster, easier, and more accurate by synchronizing automatically all of the information that you may need and giving you easy to work with and a user-friendly way to report those information. And finally, it has a modularity expansion capabilities, so you can update your system as you need it, when you need it, and benefit from all of the latest improvement without having, purchase entire new suites or anything. So I think that's it for the presentation. Thank you all, and if you have any question, please ask.
Fantastic. Thank you so much, Remy. Those videos are amazing. It's very fun to watch. So we do have some time for some questions if anybody has a question.
May I ask a question?
Of course.
Oh, thank you very much for the very nice talk. One question actually I keep receiving from other collaborators is how accurate the temperature is from the Protochips holder. How do we know that's the exact temperature?
That's a very good question. So I'm going to go back to that slide. So when we manufacture those chips, the heating element, what is actively performing the heating, is a silicon carbide technology that we patent. And it is extremely accurate in several ways. But I think the most efficient way to prove that is every single chip is calibrated by infrared cameras. So basically, imagine you purchase a box of chip, you obtain 10 chip, and within the box, you have 10 calibration file, one calibration file for every single chip. And this calibration file basically is the result of observing this chip being heated under infrared camera mapping. And every chip, we perform an infrared map of the heating element, make sure there is no hot spot, no cold spot, and that every time you ask for a certain temperature, you get that exact temperature. Once this is checked and we make sure that the quality of the chip is good, the calibration file is drawn, and when you perform the experiment later on in your TEM, you know that at every point in temperature that you use, it's been measured and tested before. And this is what we said about it, but I can also send you two references. It's two articles which have been published by one with one of our collaborators from Protochips and one was independent, and both saw the same results. They used EELS technique, gain and loss EELS spectroscopy, to measure the temperature of a sample with the TEM beam. And they obtained the same temperature with the same specification that we provide. So they confirmed the accuracy of those chips experimentally.
Okay, great, thank you. It will be nice to have those two papers. I'm very interested in using EELS to investigate or to measure temperature. That's something I didn't know before.
It's a very elegant technique, and yes, let me write down your name. I'll send you the publications.
If you want, you could send them. I think you might have Avery's email, and I can share it with the participants today, or whoever would be interested, if that's easier.
That would be great. Yeah, thanks.
Okay,
thank you.
Any other questions? If not, thanks again, Remy. That was really fantastic. And so we'll go ahead and move on to our next presentation. So we're